Today's presentation will be dealing with fecal coliform source characterization, disinfection of those waters, and then some active control strategies relative to both point and non-point kind of systems. So the first step, I think, that's very important in looking over your situation is to do what I'm terming source characterization. So source identification looks at point sources and non-point sources, basically doing an inventory, looking at the storm event behavior in terms of storm events of the season. So first storm of the season versus later storms in the season have a difference, as well as where in the storm the water is, whether it's first flush versus later in the storm event. Those behave quite differently. And I think one of the most important aspects in terms of looking at active control approaches is measuring flow, making sure you figure out rate and volume, because these are important features that you need to have when you're trying to correct a problem. So the goal is to do, for this source characterization, is to figure out your fecal coliform concentration characterization, the profile with respect to both seasonality in terms of wet weather flow as well as any dry weather flow that you're dealing with. Here are some values in terms of when you inventory your site. A typical sanitary sewer flow will have about 10 to the 7th fecal coliform per 100 mL. So if you're seeing high levels in a collection system, say 10 to the 5th, 10 to the 4th, you start thinking about perhaps you might be having a cross connection. In terms of bird surveys, this is some data we collected for swallows in my Priest Reservoir study. This converts for a swallow to be about 10 to the 8th per bird per day. So pretty heavy load from a pretty small bird. Then erosion control bales. They're using hay bales. They used over 1,800 hay bales around the watershed to prevent sediment erosion into the drinking water reservoir. We found that Klebsiella was the culprit, and we found that after being wetted, that as much as 10 to the 7th gram dry weight from the hay was the source. So the reservoir was about 100 mgd flow. So this kind of load elevated the total flow almost half a log higher. So tremendous load coming in from the hay bales. The other thing they did at this reservoir was to manage it on a daily basis to deal with short-term electrical power to sell it on spot market. So they would raise the water level in the reservoir so that by noon they could then lower it, generate electric power, and then sell it on the spot market. And what that did was it flooded portions of the reservoir in the evenings, and then repeated flood and dry cycles occurred. And when we looked at the grasses in sod that was being flooded, we saw as much as 10 to the 4th per gram of the sod material. So if it gets infected, and again, these were all Klebsiella pneumoniae, which is a fecal coliform. So if this area gets infected, the fecal coliform is a stable and gets shedded from this area. So part of doing your site inventory is to locate systems and areas within your site for the occurrence of these kinds of situations. So here's not all storm flows are equal. So we're looking at 2 storm events. The first was in November 1st, this over a 14-day period. The last storm in April of the following year. The study in Humboldt Bay, which is a little bit further south from here, rains a lot more than Southern California, from a watershed study going into the Humboldt Bay by Geis in 2003. The red line represents the 100 fecal coliform per 100 ml MPN value. And you can see that in the first storm event at the same sample location that they were quite elevated, and the later storm, basically all this material had flowed out of the system and everything was below the 100 ml fecal coliform MPN value. The next in the study compares two different sites at the last storm event. Previously it showed, it's below the 100 ml value, and the adjacent site showed that even though this was the last storm, it still had high coliform levels, as much as 1,000 coliform per 100 ml. These are all from fairly large catchment basements, structures, about 48-inch diameter drainage pipes. So this indicates that there's kind of a coliform source and possibly a cross connection into it, or some other constant load coming into the system. It doesn't taper out like the first flush occurred in the previous slide. So the characterization that you're trying to do is to do both in terms of different locations within your study area, as well as seasonality. And clearly, each year, depending on how much rainfall and those kind of issues, that you will get varied responses. So you need quite a bit of historical record to really think about how best to spend your dollars if you're going to do put in any kind of treatment system that typically requires quite a bit of money. So trying to determine when to treat, that is, in the first site, you probably wouldn't need to treat in the last storm. You probably would have to treat in the first storm. And in the second set of slides, the first site didn't need treatment. The second site probably needs treatment until you corrected the background flow into the system. So the other thing we saw was how much to treat. So again, the first storm, you might have to treat all of it, which dictates how much storage you might have to have. And storage is quite, there are various options depending on what you have already as a baseline at your facility. And you try to basically, with storage, reduce the facility, the disinfection facility, because you can flow equalize and reduce the cost associated with the disinfection side of the system. So it's a balancing act between storage and in terms of where you want to spend your money. In all cases, disinfection requires that turbidity be reduced. And different disinfectants have different requirements for how much turbidity it can be there to get the system still to meet its treatment goal. And so the part of this characterization part also allows you to figure out what disinfectant to use and the dose of the disinfectant, which relate to the sizing of the system. So in terms of disinfection, one thing it brings to the table is it brings reliability of compliance. So you can design the system so it's always under a given treatment goal. Typically, as I mentioned before, low turbidity is required. Generally, if your median fecal coliform is greater than 100 per 100 ml, some type of disinfection is required to have reliable compliance. And generally, I would recommend at least one log lower as your treatment goal than the discharge limit. So if your max, say, is 100, this means that the treatment goal should be 10 per 100 ml. And generally, all the disinfection schemes talk about when they talk about dose, we think about concentration of the disinfection times time, or in the case of UV, it's intensity of the UV radiation times time. So a CT, or concentration times time, design criteria. So for example, in reuse, the number is 1,200 milligram minutes. So you can generally achieve the 1,200 milligram minutes in a range of ways. And so one way of meeting that goal would be 10 milligrams for 120 minutes. You could go 100 milligrams for 12 minutes. That's pretty extreme, but anyway, the 10-minute thing would shorten your contact time, your storage and the size of the contactor, but you would increase the dose. So generally those two approaches would meet the same goal in terms of efficiency. So that gives the designer some flexibility. Okay, in terms of, here's the effectiveness of the various disinfectants to remove 2 laws of reduction. Here's combined chlorine. So if you had ammonia in your system for some reason, you require 100 times 100 milligram minutes. For free chlorine, it's 1 milligram minute, pretty short time. For ozone, it's 0.01, and then UV has an intensity of 10, an IT of 10. So in terms of points of application, some comparisons, UV is many. Typically UV and ozone, if you're using these, you want to only have one of those because it's pretty expensive. In terms of collecting and pumping storage, not necessarily, I'll show you some case studies there. Typically in UV and ozone, probably. In terms of residual, you must remove the chlorine, non-trace. There's some disinfection byproducts. In terms of receiving water, if you use ozone, you add oxygen to your receiving stream, so it improves the water quality. Some generalized cost, chlorine being lower than UV and ozone. So some control strategies. Source reduction is pretty important. You're looking at generally combining sources, so points of application are reduced in terms of managing those points of application. And once you disinfect it, and in certain cases, in ozone and UV in particular, if you go down that road, because they're so expensive, you have to think of how to reuse that water so that it's a beneficial, so you reduce your cost for multiple benefits. So disinfection with UV ozone, looking at those first. So you have to reduce turbidities. You can use BMP type things like swales, or traditional approaches like screening, membranes, granular media, filtration. Storage, there are a number of ways to store. BMP type storage or traditional tankage. So next, there are 2 municipal treatment systems, one by the city of Santa Monica, 500,000 gallons per day. From the storm drain through here, this is all for turbidity removal. And then here's a UV disinfection system, and then the reuse of the water for landscaping or indoor commercial indoor flushing. Pretty expensive, $12 million for 500,000 gallons per day. And that system came on board at 2001. A different system using ozone for the city of Malibu. They're taking water out of a creek at 1,400 gallons a minute, the first flush part, and then typical drive of the flow from 250 acres. Pretty simple process, screening, filtration, ozone. Again, relatively expensive, $5.3 million. This is comparable to a full-scale water treatment plant in terms of gallons per minute and cost. And end use of the water, irrigation, and constructive wetlands. So If you're trying to do centralized flow, here's a methodology where they're using, some, you can't see this, but anyways, plastic low fencing, followed by some straw systems, trying to get everything flowing over this bare land into the storm culvert. So now you can treat the culvert instead of whatever's flowing over to the street. So here's a little close-up of the straw material in a netting form, and here it's in application, and here's the flow, so you're kind of filtering the flow out before it gets down, and this runs into a surface reservoir. So these are some BMP type things at work, but you have to recall that the straw and grass could be a source of fecal coliform. Here's an industrial application, and they've allowed the material, as long as it is effective in terms of diverting water to where they want it to, this probably has quite a bit of bacteria in it as it ages. So here's a application of using wetland filtration and storage with UV disinfection from a project in New South Wales, Australia. So they're going to wetlands for the filtering and getting the sediment out, and then UV for irrigation. So these structures here do two things. One is filter, and then they also allow storage. So lessons learned. In terms of the first part of my talk, talked about trying to identify hotspots of materials that would be causing some fecal coliform, trying to eliminate cross connections, and housekeeping reduces fecal coliform concentrations, reduce rodents and birds in terms of the sources, understanding the storm events, and then meeting the discharge requirements, trying to determine if disinfection is needed. And if it is needed, then you have to look at some of the pretreatment needs, storage, turbidity reduction. And if you're using chlorine, typical smaller systems, as opposed to UV and ozone, you normally, because they're so expensive, you want to use larger systems for this technology. Chlorine is much easier to adapt to existing infrastructure. There's more available low-tech tools. So if you go to your catalogs, there are pellet ways to add chlorine via pellet methodologies, pellet ways to neutralize the chlorine in place. You can use some very low-tech approaches relative to putting chlorine pellets in bags, suspending them in collection systems, putting pellets in a bucket and neutralizing the chlorine from the collection system in that manner. But one thing to remember, this is, even though it's more easy to install in a existing collection system, you do have to dechlorinate, and you have to dechlorinate carefully, because in some cases the dechlorinating agent also takes up oxygen, so you could deoxygenate your receiving water if you over apply the dechlorination agent. So you have to be careful about how that aspect is sort of dealt with. With that, I'm open for questions.